Hi, today we will present explainable pneumonia classification from chest X-ray images. According to recent studies, pneumonia diseases caused almost 50,000 people in the United States to die each year, a major evidence to the importance of diagnosis. Although early diagnosis is possible by doctors using CXR, it's a great burden for them to evaluate these CXRs from scratch because it's time-consuming and labor-intensive. Thus, availability of expert radiologists, especially in low-income countries, makes early diagnosis inaccessible. In order to avoid this, CAT systems can help naive doctors to navigate and have some insights from an X-ray images. In this work, we investigated pneumonia detection in chest X-ray images. Here, we introduce our datasets, pre-processing steps, experimental settings and designs, results, and intuitive explanations of our models. The dataset is formed by Radiological Society of North America by benefiting chest X-ray 14 datasets in order to diagnose thoracic diseases. Where this dataset differs from chest X-ray 14 is that the images are shared in DCOM format, and the datasets is arranged so that it can be used to diagnose pneumonia in particular. DCOM format consists of pixel values of X-ray images as well as the metadata that belongs to the images. The dataset contains nearly 27,000 images, where each one is labeled either not normal, no lung opacity, normal, and lung opacity. Normal label represents neither pneumonia nor any other conditions detected in the image. Not normal, no lung opacity represents opacity in the X-ray image is caused by a condition other than pneumonia. Hence, it is related to any other conditions. Finally, lung opacity represents opacity in the image caused by pneumonia. Opaque areas are segmented by radiologists using bounding box technique. Distribution of the labels are shown here. During pre-processing steps, we applied pretty standard pre-processing steps for our experiments. Because the dataset is imbalanced, we randomly sampled 8,800 images from each class and trained our models. We read images as DCOM format and then performed pre-processing steps, which are resizing them to 224 by 224, cropping their centers, flipping horizontally, and rotating them up to 10 degrees randomly, respectively. We finally normalized images according to the ImageNet mean and standard deviation. Visualization of our process can be seen as follows. We conducted various experiments. Firstly, we chose two fundamental deep neural network architectures, DenseNet and ResNet. We approached the problem as a binary classification problem and trained these neural nets with RSNA pneumonia dataset. Then, salience maps acquired from GradCam and LayerCam techniques were generated. Next, in order to determine if these salience maps were learned based on our binary problem or not, we designed an experiment that differentiates learned neural nets from randomly trained ones. Our hypothesis was that the more the difference between them was high, the likely the salience maps were generated according to our problem. Finally, so as to measure how non-lung areas of chest X-ray images change our salience maps, we trained a deep lung segmentation model and passed X-ray images to it. After the lung mask was detected, we colored non-lung areas black so that our deep models could not learn anything from those regions. We followed the best practice of medical image analysis and chose DenseNet and ResNet architectures for our experiments. In order to see the impact of salience maps, we simplified the problem as we chose only two classes, normal and lung opacity. Binary cross-entropy lung loss function is used as a loss function. Networks take three-dimensional 224 by 224 chest X-ray images and outputs a probability of how likely the image is lung opacity. Our optimization algorithm was ADA delta with default parameters of PyTorch framework. We trained models for 50 epochs using batch size of 16. In order to segment lung areas of chest X-ray images, we used UNet model, whose encoder part was the feature extractor of VGG16 architecture. During training, Dye's coefficient was used as a loss function. The model takes an image of size 448 by 448 with 3-dimensional and outputs an image of the same size. In this way, we took advantage of the ImageNet pre-trained VGG16 feature extractor. The model was optimized using Adams' algorithm with default parameters. Various datasets are combined for lung segmentation task. The reason behind it was that the number of lung segmented images is not that common. Details of these datasets can be found in the report. We used the lung segmentation model to have a lung mask of the feed-forwarded chest X-ray images. Then we combined these masks with the corresponding X-ray images. Thus, non-lung areas are colored black. Then we follow the same procedure as in the previous experiments. First table presents results for lung segmentation model. Results are promising in terms of segmenting lung areas in X-ray images, even for various datasets. Second table presents results for our classification scenario for different networks, different labeling techniques, and lung segmented support. Models using segmented CXR images presented better results than the models that use segmented images. There was no superior relation between models with or without lung segmented support. Both settings were on par in the normal class. In all cases, the models using segmented images performed similar, considering the selected metrics. That result alone might discourage the usage of segmentation in practice only in terms of classification. Figure here shows the difference between the randomly labeled model and the correctly labeled model. Since learning did not occur from the randomly labeled model, random models, the class heat maps almost did not focus on the lung area at all. Here we see another example of the salience maps generated by our models. The threshold value have a critical role in measuring the GradCam and LayerCam methods. The success rate varies according to the threshold value determined. Performing performance analysis using equal and frequent intervals is very costly. Testing a threshold value with each model takes approximately 2 hours. Since there are 6 models, this period takes 13 or 14 hours in total. In order to minimize this cost, 5,000 images were analyzed. We aim to determine the threshold value ranges, start and end points of the images according to the pixel distributions. We observe that there is a distribution between 100 and 200 pixel values according to the histogram distribution. The rate of change was determined as 25 pixels. Therefore, analysis was performed using values of 100, 125, 150, 175, and 200. Here you see some samples from our test datasets and their corresponding salience maps. To sum up, in this work, we presented the first benchmark between salience maps and bounding box disease localization. We showed that different architectures can result different salience maps. Lung segmentation can help our models to generate more interpretable and robust maps. We also proved that the more the models learn a given problem, the more interpretable and meaningful results that they generate. This work fills a significant gap in terms of presenting a new benchmark to the literature, doing a comprehensive experiments, and being a first step of a wide variety of further improvements. Thank you for your attention.